Okay, here's a projectile motion problem for you. We got a golfer hitting a golf ball toward a wall. I doubt if that's very good for the wall. Let's draw a picture of this situation. We'll get golf ball starts off over here. Person hits it, giving it some initial velocity at an angle of 29 degrees above the horizontal. Having a magnitude, I'll call that V0, of 33.0 meters per second. So let's indicate the horizontal in this diagram. And then this angle in here is given as 29.0 degrees. Alright, hits a wall. Consider it a vertical wall facing the golfer, and the wall is a distance, I'll call it x, equal to 52.0 meters from the initial position of the ball. And the question is, how high up on the wall does the ball hit? So this object probably going to follow a trajectory, something like this. And they're looking for the value of y. Say it hits right there. They're looking for this value, where I'm going to choose this initial position of the ball to be the origin of my coordinate system. So this will be the x-axis, and this will be the y-axis straight up. If we think about it for a second before we get started, we can see that, assuming that it does make it as far as the wall before it hits the ground, the x motion, how far over it's traveling, is going to determine the time of flight. Note, if we get a negative value for y, that would suggest that it doesn't make it all the way to the wall. That would correspond to a trajectory that took it something like that, and we could say it never hits the wall if we do get a negative value for y. But okay, we got an idea what's going to happen. Let's get started on it. Remember, we have to consider the x motion and the y motion separately, but v0 corresponds to a velocity that's partly forward, partly in the x direction, partly in the y direction. So to get started, we have to break up v0 into its x and y components. So get a little vector component diagram going for the vector v0. Indicate v0 at the 29 degrees. Draw in an x component starting at the tail of that one. If I go along the x-axis, I have to go this far before I get to a point where a vertical vector added onto that one will give me the total velocity v0. So I'll call that v0y, v0x. Let's see, v0x divided by v0 would be the cosine of theta. So v0x multiplying both sides by v0 is just v0 cosine of theta. So that's 33.0 meters per second times the cosine of 29.0 degrees, or v0x, is 28.86 meters per second. And I am going to keep an extra sig fig in my intermediate result here, but I'll round off the final answer to 3 sig figs. Everything was given to 3 sig figs. V0y divided by V0 would be the sine of theta, the opposite over the hypotenuse. Multiplying both sides by V0, I get V0y is just V0 times the sine of that angle theta. So V0y is 33.0 meters per second times the sine of 29.0 degrees, or V0y is 16.00, if you wish, meters per second. So that's V0y. It's actually good to 4 sig figs, but I'm going to just write it as 16.0. And V0x over here. Now, let's start with the x motion. There's no acceleration in the x direction, so x is just x0, which I claimed is 0. Started the golf ball at the origin, so it's just V0 x times t. Now I want to know how high up on the wall, so I need to find the time that it takes to get to the wall, where the distance x is 52.0 meters. So I'll solve this equation for the time of flight. At 52.0 meters divided by what we found for V0x, 28.86 meters per second. That's how fast it's moving rightward, or toward the wall, rightward in our diagram. And that yields a time of 1.802 seconds. To, again, one too many sig figs. Now for the y motion, I have called the upward direction the positive direction, and the acceleration in the upward direction is actually minus 9.80 meters per second squared. Let's make a little more room for that. So I'll call that a sub y. The x motion from our first constant acceleration equation, but replacing the x with a y. So I mean, for the y motion, we got y is 0 plus v0yt plus 1/2 a sub y t squared. Okay, we started off at ground level, so y0 is clearly 0. Did have some velocity and definitely has some acceleration. I think we're in a position to go ahead and analyze that. We know everything. Just substitute values and evaluate, I should say. 16.0 meters per second times the time that we just found, 1.802 seconds, plus 1/2 of our minus 9.80 meters per second squared times that same time, 1.802 seconds, all squared. Substituting that into the calculator and evaluating, and I'm going to go ahead and round it off to 3 sig figs. I get 12.9 meters for the height above ground level at which the ball hits the wall.